Alright class, today we're going to start 10.4, which is motion in space, and we've kind of been hinting at this the last couple of days. We're looking at our vector function r of t as to give us the position as a function of time, r prime of t, which would be the derivative of your position. Of course that gives you velocity as a function of time, and if you need the speed would be the magnitude of your velocity function. And r double prime of t is the rate of change in your velocity, which of course would give you your acceleration. And so those are the three basics. They should be fairly familiar. It's the same concept that we've worked with since Math 151, but in this context though we're dealing with vector functions instead of just a function of a single variable in there. So let's do an example. So suppose that we have r of t is equal to 2 cosine t, 2 sine t, and let's do how about 3t? Alright, and then so that gives us our position as a function of time, and if we're looking for the velocity, we're just going to take the derivative of our acceleration. Our velocity vector will be the derivative of our position vector, and so that would be minus 2 sine t, since the derivative of cosine is minus sine. The derivative of sine is cosine, so I'm going to have 2 cosine t, and the derivative of 3t will just be t. Will give us our velocity, and if we need it, the speed that we're traveling, which is how fast you're going without any sort of direction involved, that will be the magnitude of our velocity, so the square root of minus 2 sine of t squared, quantity squared, plus 2 cosine of t squared plus 3 squared. So it will be the square root of 4 sine of t plus 4 cosine squared t, sine squared t, cosine squared t plus 9. You can factor the 4 out, so we'll have 4 times sine squared t plus cosine squared t plus 9, and sine squared t plus cosine squared t is that trig identity. It's 1, so I'm looking like the square root of 4 plus 9. The speed would be the square root of 13 in whatever units that we have for our function. If r is measured in meters and t is measured in seconds, that would be 13 meters per second. If it's, well, that's probably what it's going to be. And then a of t, if we needed our acceleration vector, we could just take the derivative of the velocity, and so derivative of velocity, derivative of minus 2 sine t would be minus 2 cosine t. The derivative of 2 cosine t would be minus 2 sine of t, and the derivative of 3 would be 0. So our acceleration vector is this minus 2 cosine t, minus 2 sine t, and 0. Alright, and then we can also go the other direction if we want to. If we start with acceleration, like if we look at projectile motion. If we start with, so suppose we fire a projectile at a 35-degree angle with a velocity, well, with a speed, we'll say a speed of I don't know, 40 meters per second. 40 meters per second, and we want to describe the path of the projectile. By that I mean find a vector function goose that models that. So let's assume that I think we can get away with just working in 2 dimensions here. So we're going to fire this initial with an initial velocity here of 40 meters per second at an angle of elevation of 35 degrees. And so if I'm working in 2 dimensions, if I'm working in x and y, we'll do just x and y there. What I have is that the initial velocity is going to have some sort of horizontal component here. It's going to have a horizontal component that is, let's see, that's the adjacent side. I know the hypotenuse is 40. So if I look at the cosine, that's the adjacent over the hypotenuse. So what I get is that the initial velocity would be 40 times the cosine of 35 degrees. And the initial velocity, or the initial y component would be 40 times the sine of 35 degrees. Alright, so that's our initial starting velocity. Initially we have an acceleration, and the only acceleration we're going to go with is that we're going to assume that gravity is pulling downwards at some sort of force, so minus g. So if we're looking in meters per second, I think it's what, negative 9.8 meters per second. So this is our vector function, which would be 0 minus 9.8 meters per second squared. Alright, and so if that's our acceleration, then I know that velocity would be the antiderivative of the acceleration vector. And so when you take the antiderivative of 0, you're going to get 0 plus some constant, right? Because you're going to do term-by-term antidifferentiation. The antiderivative of minus 9.8 would be minus 9.8t. Oops, not t squared, t. Plus some other initial constant. How about c sub y? Let's make this one c sub x and c sub y. Alright, and I also know that v of 0, if you plug in 0 for t, you'll just get c sub x, c sub y, and I know that that's got to equal my initial velocity of 40 cosine 35 degrees, 40 sine of 35 degrees. Alright, and so my velocity function is actually, as a function of time, not just at time 0, as a function of time, it would be 40 cosine of 35 degrees minus 9.8t plus 40 sine of 35 degrees. And then if we're looking for position, we're going to take the antiderivative of velocity, and we do that term by term. So I'm going to get 40 cosine of 35 degrees times t plus, again, some constant, some, let's say some r0, or x0, let's go x0, some unknown x constant, and then our antiderivative on the y value would be minus 9.8t squared over 2. Add 1 to your exponent, divide by your new exponent, plus 40 sine of 30 degrees t plus some initial y coordinate there as well. And if we're looking at this as being fired from the origin, then your initial y coordinate and your initial x coordinate and initial y coordinate are 0. So it's probably something like this: 40 cosine of 35 degrees times t for the x component, and minus 4.9 t squared plus 40 sine of 30 degrees t. And again, if we're assuming that your initial position you're initially firing from is 0, 0, x0 and y0 would be 0. And so there we would have our position as a function of time. Alright, the next lecture we're going to have is going to be about acceleration. the t vector and the n vector. But we will save that for a new video.